I will always print it and grade it. So what I want to do today is to think about.
This screen is not.
Oh yeah, I have to do that.
I can't find mine.
What's your name?
Shubhadeep.
It's there somewhere. Someone else took
is
it.
it today
Don't stress out. Yeah. If you don't find it, come in the middle of the class. Maybe someone else took it. Your grade is noted. Except jocks, everyone's in an undergrad. You shouldn't worry about this anyway.
Got it.
He's freaking out. Don't worry. So, okay, let's start with Sawadeep. Sawadeep, I need your help. I want to write down DE in 3 different ways today. Okay? I want from you expressions for DE in 3 different ways. Shubhadeep, can you tell me the first one? DE is internal energy. So tell me an equation for DE.
PDS minus PDV minus new.
Minus or plus?
Plus
Huge difference, right? So, okay. So he started with what I would call the third equation. But I'm looking for 2 more. What else? Go ahead.
Delta Q plus W.
Delta Q plus delta W. And a second one, which is kind of harder. Can we think of a second, I mean, in this case, a third equation for DE? That is somewhere in the middle. Your hint is it's similar to this one. It's closer to this one. That's fair enough. So I would write this one as equivalent. Yeah, that's the first one, right? So I would write this one as minus P external dV plus mu external dN, right? So that falls in the same category. The middle one I would say is dE is equal to partial E by partial S constant NV ds plus partial E by partial V constant NS dV plus partial E by partial N constant SV dN. Now you might say second and third are the same, but they are not really, right? We had to do something to go from second to the third, right? So my next question for you is the names of these 3 equations. What would you call the first one? What is the name of the first one?
First law.
That's first law of thermodynamics, right? And since I have you, tell me the name of the third one. Yeah?
I'm choking on the pressure.
It's okay. Have you read the book Novel Choke by Chuck Palahniuk?
No.
You should read it. Maybe. Yeah, go ahead.
Integrated first and
It's the integrated first and second law. And how about the middle one? That's just second law. So in thermo, I will be recapping material again and again and again because there is really not a lot to do in thermo. 1 second, Anjali. If we understood everything, we could finish the whole semester in 1 week. But we don't, right? It's complicated. So we have to go over everything again and again. Go ahead, Anjali.
I was just curious about how the second equation, isn't that the second one, the adiabatic attributes always positive?
Sure. The second law had many statements. One of them was that S is equal to S of E and V is thermodynamically complete. Together with the monotonicity condition, right? That partial S by partial E at constant NV is positive. So the fact that you can write down DE is in this form has exactly the same information as everything in the second law except that one, the part that you said that for an adiabatic process delta S should be positive, right? So it covers almost all the postulates. So let's call it Court's second law. It's missing some information. The third one, on the other hand, is integrated first and second law, right? Because if you think about it, how did we derive the third one? You did it in your second homework, right? We wrote down the second one, and then we said that if we define the thermodynamic temperature as partial E by partial S, it has the same behavior as the physical temperature, right? In order to do that, we considered a box which was isolated. And if you go and look at your proof, you assumed first law of thermodynamics while doing that. If the box is isolated, delta Q is 0, delta W is 0, and you assume that this means delta E is 0, right? So you used first law of thermodynamics, you used conservation of energy, right? So So keep this in mind that there are 3 different ways of writing DE. They all have different information. If you want to forget everything, you can just remember the integrated first and second law, because that is most powerful. The second point I want to make right now is they are the same DE, right? If you're interested in a system going from state A to state B, if you define DE as EB minus EA, you could take a reversible path, you could take an irreversible path, you could do whatever you do, right? The difference between the energy in the starting point and the final point is going to be the same. That does not matter. So we can write down DE in these 3 different forms, but it's the same DE as long as the endpoints are different. Same, as long as the endpoints are well defined, as endpoints are integrated. So what does this allow us to do? So again, let me write down. So same, okay? If endpoints are same. This is because energy is a state function. Could I say something like that about Q? No, QB or QA does not make sense, right? Q is always delta Q. I cannot say like, what is the work of Shah today, right? It does not make sense. I could say, what is the internal energy of Shah today, right? I would model Shah as an ideal gas. Are you okay with being modeled as an ideal gas? If you don't like it, we can model you as a van der Waals gas, right? But I could calculate the energy using that. But instead, if you said, what is the work of Shah? That does not make sense. It would make sense to talk about the work done on Shah as we take him from some state A to state B. And which pathway do you take? That makes a whole lot of difference. So another thing to remember very carefully is that delta Q is heat given to the system. Delta W is work done on the system. So it's a very system-centric point of view. We are looking at what's happening to the system. Many books defined it is the other way, and there is nothing wrong in it. But you have to be careful with sign convention. So since these DEs are the same, what we can do is to compare them. So we can take DE is equal to delta Q minus P external dV plus mu external dN. And we can take DE is equal to TdS minus PdV plus mu dN and say they must be the same if the endpoints are fixed, right? Further, if we assume a reversible process, what is that? Under equilibrium, then P external is equal to P and mu external is equal to mu, right? It's a reversible process under equilibrium. In that case, we can take this equation and write it as delta Q reversible. We have to specify that now it's we are calculating the heat given to a system in a reversible process. Minus PdV plus mu dN is equal to TdS minus PdV plus mu dN, right? So what can we do now? We can cancel out minus PdV plus and plus mu dN from both sides, right? So what are we left with? We are left with ds is equal to delta Q reversible by temperature. I'll call this equation number 1. This is a super important equation. Why? Because for the first time, we started thermodynamics by talking about very abstract things, right? That there exists a function S which depends on NVE. What does that mean, right? It doesn't tell us how to do something. This equation is super nice because it tells us how to calculate change in entropy, right? If we knew how to measure the heat given to a system and we calculate how much heat did we give it, as long as we do it reversibly and we divide it by temperature, we can calculate the entropy change. So all of a sudden, entropy has become something concrete that you can measure. Not the entropy itself. I still cannot answer what is the entropy of Shah. You are going to be my model today. Is that okay? Good. Because we have same hairstyle. But this allows me to talk about what is the entropy change of Shah, right? But in order to do this, I have to heat up Shah reversibly. That's not going to happen, right? He's going to get angry if I try to heat him up. It's not going to be a reversible process. So while this equation is really nice, it puts entropy in a realistic, concrete setting. It still does not get the job done quite as we would like to, because delta Q reversible is dangling on the right side, right? So it's nice to think, well, what is the relation between ds and delta Q irreversible divided by temperature? It would be amazing if those two were also the same. Sadly, they are not, right? Turns out, we saw last time that ds is more than delta Q irreversible by 2. And this is known as Clausius inequality. This one tells you that if you want to calculate the entropy change in a system, and if you were to give heat to it very, very slowly in a very reversible manner, and that's a limit you can never attain, right? Anytime you heat is for construction dissipated, right? It just disappears. You cannot do it reversibly, it will disappear. But if you were to do it very, very slowly, you could calculate delta Q reversible by temperature, integrate it to get your ds. Anytime you give some heat and it's irreversible, you do it at a finite rate, your entropy change will be more than delta Q by T. So it's giving you a lower bound for the entropy change. Using this inequality, you can calculate my entropy must have gone up by a certain amount, okay? I'm going to work through the proof of this Clausius inequality once again today in class, because that required that reversible work and irreversible work thing, and I think it's important to go through it. The third homework will have some problems, which will help clarify that for you. But before doing that, I want to talk about some nomenclature and make sure that we are all on the same page. So, yeah, please.
So the second law, the expression we got for the energy came from the postulate and mechanics. And then the first law comes from the definition of thermodynamics.
First law does not come from a postulate. That is pre-postulate. That's conservation of energy.
And then we say, because the two delta is are the same, we could say equality for each term. But how do we know that from the thermodynamic perspective, we're not missing any additional term?
We are not missing anything because the postulate did tell us that S of NVE is complete. You cannot miss anything. It has said that for you. It has erased exactly those worries for you. Okay? Keep thinking about it. It's almost a philosophical class. You will gain very practical things by the end of this class, but you will also have deep philosophical questions. Like that is the goal. Yeah, but good point. It's really because we are saying that S of NVE is complete. You can characterize an equilibrium system completely by NVE, and S is maximized. That's where it comes from. So what I want to ask you now is, for our understanding, let's ask some questions. Murray, the first question is going to be for you. Is that okay? I'm not giving you much choice, sorry. Okay, Murray. It's an easy one. What's the meaning of an adiabatic process? No heat exchange, right? So in terms of Q, what can we say? 0, right? Correct. So adiabatic means delta Q is equal to 0. It doesn't have to be reversible or irreversible, right? What is ds for reversible adiabatic process? 0, using equation 1, right? Because it's delta Q reversible. What is ds for irreversible adiabatic process? Huh? Who said 0? Are you sure?
Am I wrong?
Yeah. No, that's why I'm doing it. It's trippy. It's confusing. I said irreversible. So even though it's adiabatic, now I have to use equation 2. I cannot use the equation 1. No, these things are very, don't quote me, but a lot of professors would get these things wrong. It's even in our department or anywhere, because it's subtle, right? They confuse terms with each other. So you have to be very, very careful. Okay, would you agree now?
Yes.
Good. So all we can say is that for an irreversible adiabatic process, entropy change is more than 0. And physically, what does it mean? It means that you have a box which is isolated from the world. Heat cannot go out. and you put the coffee on top of the box, right? It will just fall down and equilibrate and everything, and the entropy went up. Even though it's isolated, the entropy of the system can still go up, right? Because an irreversible process is happening inside it. The second thing I want to point out, which the number of people who confuse these two things is like 99% of the planet. I think that's a fair guess because 99% of the planet does not know thermodynamics, right? So it's definitely more than 99%. The second term I want to talk about is isentropic process. So often people, even students of thermodynamics, whoa, look at that. Confuse adiabatic with isentropic, but they are not the same, right? Isentropic means ds is equal to 0, okay? An adiabatic reversible process is isentropic, right? A reversible adiabatic process is isentropic because ds is equal to 0. An irreversible adiabatic process is not isentropic, right? It cannot be because ds is going to be more than 0. Can we think of, so we know that a reversible adiabatic process is always isentropic. Does this mean all isentropic processes are reversible adiabatic? No, right? What do you think? Why? Can you think of an isentropic process which is not reversible adiabatic?
Not, but by intuition, it seems that there must exist an isentropic process.
She's confident. We will believe in her confidence. Okay, but we will come back to. We will see many examples of processes like this, right? So these are two terms that show up a lot. A lot of people use them interchangeably. Be careful, right? Because the difference comes. If the world was reversible, then yes, they would be the same, right? If the world was reversible, then ds would be delta q reversible by t, and isentropic would always be same as adiabatic. The world is not reversible. Time is flowing in one direction, right? So we cannot do that. The other terms that we encounter a lot are isochoric. What does this one mean? No change in volume. dV is equal to 0. Then we have isobaric. dP is equal to 0. Then we have isothermal. dt is equal to 0. Later, we will see more examples of things like isenthalpic and others. Okay, so these are the 5 that there exist. These 3 are easy. The confusion always happens between adiabatic and isentropic. So remember, adiabatic is not the same as isentropic unless the process is reversible. If the process is irreversible, they are going to be different. So let's try to prove. Any questions about this before I go further? Okay, so let's try to prove Clausius inequality once again, that ds is going to be more than equal to delta q by t, where the equality holds, equal holds if reversible, right? So this is a general way of writing it. Okay, so the proof is very similar to how we derived the reversible case, right? So how did we do this? In order to derive the reversible case, we compared 2 forms of dE, right? So let's do that once again. So we will say that dE is equal to delta Q irreversible plus delta W irreversible. Again, let's use Shah as an example, right? I have to transport Shah from this floor to the floor above, and I do it in a very irreversible manner. We all get together and just punch Shah through the roof, and he gets there in some irreversible manner. Or we are very nice to Shah, depends on the day, and we do it in a very slow, gradual manner, right? We really drag him like a gentleman and take him to the floor upstairs, very reversible. In that case, it would be delta Q reversible plus delta W reversible. But the net effect of Shah on Shah is going to be the same, right? Once he equilibrates on the floor above, the dE would be the same, right? That's the point. If the endpoints are carefully defined, then you're careful. In practice, often these things end up being the problem. You're not careful with equilibrating your system at the endpoint and things like that. But otherwise, these two are going to be the same. Okay, it does not matter whether you did it reversibly or irreversibly. So once we have this, what can we do now? Let's write this as delta Q irreversible plus delta W irreversible. Can we substitute something for delta Q reversible? That is TDS, right? TDS plus delta W reversible, or TdS is equal to delta Q irreversible plus delta W irreversible minus delta W reversible, or ds is equal to delta Q irreversible by temperature plus 1 over temperature delta W irreversible minus delta W reversible. Okay, so notice here that delta W is the work done on the system. Okay, it's not work done by the system. Last time we showed, and I will go through that proof once again. Last time we showed that work done by the system is maximum for reversible process. So if you have an expanding gas and you want to see how much work did you get out of the expanding gas, it's going to be maximized if the gas expands reversibly. If the gas expands, and we had two conditions, remember, the gas just went slowly from one volume to other, and the second one, it just went boom. So work done by the system, we showed last time, and I will do it again, is maximum for reversible process. But this is work done by the system. What is the connection between work done by the system and work done on the system? A minus sign, right? So in our lingo, this means that minus delta W reversible is more than equal to minus delta W irreversible. Okay, I will prove this again on the next page using that PV diagram. But for now, if you keep by what I have written over here, this means that delta W irreversible minus delta W reversible is more than equal to 0. And that is exactly this thing in the bracket over here, right? This proves that ds is more than equal to delta Q irreversible by T. And that's your Clausius inequality. So even if you forget this proof, that's okay. What you should not forget is the Clausius inequality. That ds is more than equal to delta Q by temperature. Equality holding only if the process is reversible. Okay. How did we prove delta W reversible is more than equal to minus delta W reversible is more than equal to minus delta W irreversible? I will just sketch the proof. That's page number 3. We looked at a PV diagram, and we had gas at a certain configuration, Pi, and it had to go to a certain configuration, Pf. And in one way, we allowed it to go very gently, reversibly from Pi to Pf. And then the other way, so this is a piston, right? The piston has high pressure. The gas is packed like this. And then in the reversible way, we gently, very gently lift the piston. So gently that at any point it could go in the other direction also, right? So that's the red curve. That's reversible. In the irreversible case, we just lifted it, boom, like this, right? So we lifted it, and then the gas is like, wait a minute, there is a lot of vacuum. Now I have to do something to get there, right? And so now the gas expands at this other pressure. And if you, this is why I also wrote down the formula for dE. Remember, the work done is P external. It has nothing to do with the fact that the gas is knocked out of equilibrium. We don't care. The P external is well defined, right? So in the reversible case, the P external is gradually changing from Pi to Pf. In the irreversible case, you drop it down to Pf and then you change it, right? And we saw that this area, is smaller, right? You can see the area of the blue curve is smaller than the area under the red curve, right? And the area under the blue curve is minus delta W irreversible, right? That's how we got it. So take home from all of this is ds more than equal to delta Q by T. Equality holds for reversible process. So at this point, if you are like me, this should make you emotional. It's like an emotional roller coaster. Because you defined S, you're like, oh, it's also abstract. I can't do anything with it. My life is ruined. Then you come up with ds is equal to delta q reversible by t, and you get excited, right? So finally, I have something for ds that I can measure. But then you get again sad because it's delta q reversible. Then you show something for irreversible, and all it tells you is that delta ds is going to be more than delta q irreversible by t. How much more? It doesn't care. 10 times more, 20 times more, 40 times more, right? It's just a lower bound, right? It's like saying 1,000 is more than 0. Doesn't help, right? So we have an emotional roller coaster going on, right? We don't know what to deal with it. So what I'm going to do next is to show you that in two specific conditions, path functions start to behave like state functions. And that's kind of powerful. We won't get all the way ds, we cannot solve the problem. All we can say about ds is that it will be more than delta q. But I will show you some nice things about delta q, which will make you feel a bit happier about things, hopefully. I want to make one more comment before I go into that, is to just use Clausius inequality in an example or an application. Let's say we have a chemical reaction happening. A plus B going to C plus D, okay? And in case one, let's say this chemical reaction is happening in an isolated condition. So isolated condition means delta Q is equal to 0, right? You're not giving any heat to the system. So in this case, if I told you that SA plus SB is less than SC plus SD, right? Because entropy is a state function. So we should be able to measure it. And later we will develop methods how to measure it. If I told you this, what does it tell you? Whether the forward reaction is preferred, like the black arrow that I drew, or the backward reaction is preferred. You are Benjamin, right? Benjamin, what do you think? Why? Entropy is maximized in forward direction, right? So we always want to go in. We know that ds is going to be more than equal to delta q by t. And in this case, delta q is 0. So ds more than equal to 0, right? So the forward direction will be preferred. On the other hand, so this means forward direction preferred. At the same time, if instead, if we had SA plus SB more than SC plus SD, then the reaction would go backwards, right? It would try to prefer A and B. And you can see this is your origin of chemical equilibrium, and it's going to show up later, right? This is how you define equilibrium constants. Now, this is in an isolated system. We could think about case 2, where it's not an isolated system, right? You have a reaction happening in this container, but now you can give some heat to it, which is many typical chemical reaction, right? You're heating the system. You can do the same thing now. What you need to do now is to compare SC plus SD minus SA minus SB with delta Q by temperature. If this holds true, then forward direction will happen, right? So already we can see why this might be useful, right? You can look at a certain chemical reaction and say, what is going to be the preferred direction? Which direction is the reaction going to go in, okay? Good. Any questions? Okay. So let's talk about heat, which is really the core of thermodynamics, right? It's thermal. So the first equation through which heat enters our framework is the first law of thermodynamics, right? Just conservation of energy. dE is equal to delta Q plus delta W. And this equation says that E is I mean, it's implicit in this equation that E is a state function while Q is path dependent, W is path dependent. Okay? Yeah, go ahead.
So in the previous slide, how do we measure DQ for the?
We are controlling how much heat did we give. So you have an air conditioner running, you have a furnace running. You can look at your electricity bill and calculate how much heat did you give.
Yeah, but that is the surrounding,
Mhm.
that's the heat bath.
That's the heat
How
bath.
much the reaction consumes from the heat bath,
Mhm.
there's no way I can control that.
You can by measuring the heat capacity and doing that. At this point, I'm saying, let's say you knew how much heat had been given, right? Let's say you knew. Yeah, and we will develop that. That's why I'm developing all this machinery. For now, I just said, let's say you knew how much delta Q was given. Okay, so good point. So how do we control delta Q, right? How do we calculate delta Q? What do we do about it? So what's this equation number? I don't know. Equation 1, 2. Well, let's call it equation 3. So let's write down equation 3 only for pressure volume work for now. Then it becomes minus P external dV. So it's kind of hopeless, right? It does not tell us anything how to calculate delta Q, right? Which is kind of what the point Shah was making, right? I don't know what to do with delta Q. I'll show you there are two specific cases in which delta Q starts to behave like a state function. And you can calculate delta Q just by looking at the two end states of a system. There are two specific cases where this happens. First one is easy. The second one will allow us to introduce a new state function today, which is known as enthalpy. And enthalpy is definitely something which is 99% of chemistry graduates 10 years after their chemistry degree will not be able to tell you what is enthalpy because it's abstract. You forget about it. And today we will spend some time trying to understand it. So there are, and I'm not saying can't be other cases, but there are at least two cases in which delta Q behaves like a state function. First case should be screaming at you from equation number 4. Equation number 4 says, and I'm going to ask Maryadala this question. Okay, Maryadala. dE is equal to delta Q minus P external dV, right? And I want delta Q to look like a state function. State function means something that can be written with a D, right? D of something. What should I do in equation 4 that delta Q starts to look like a D of something? Even simpler. Hint is volume. What would happen if the volume was constant? Even simpler. If the volume was constant, what does it do to dV? Constant volume process means dV is equal to 0, right? So constant volume means dV is equal to 0. If you said dV is equal to 0 in equation 4, what do you get? dE is equal to delta Q. That's kind of amazing, right? This is telling you for a constant volume process, again, let's go back to our model for the day, Shah. If you could make sure that Shah is at a constant volume, yeah, I mean, it's probably a good assumption. Then it does not matter. The total heat that you have to give to Shah won't matter. Whether you do it reversibly, irreversibly, it won't just matter. For a constant volume process, the total heat that you give to a system will depend only on the endpoints. So it's a simple result. We derived it in one line, but it's kind of fascinating, right? That you can do something like this, right? Equation 5 for constant volume. Reversible or irreversible. And I will put 3 exclamation marks there because that's really amazing. In other words, delta Q, constant volume, reversible or irreversible, is equal to dE. Just basically equation 5. Okay. So that's one case in which the heat, even though it is a complicated path function, becomes a state function, constant volume. The second one is non-trivial. Turns out that at constant pressure also heat is a state function. Constant pressure, which is dP is equal to 0, delta Q, constant pressure, reversible or irreversible, or any path. It could be, because it's a path function, right? And we saw a couple of classes ago that different paths, even if they are all reversible, can give you different values, right? Because there is not just one reversible path to go from point A to point B, right? This one happens to be D of something we call H. This H is the first time we are seeing enthalpy in our course. H is defined as E, the internal energy, plus pressure multiplied by volume. Is H a state function? It is, right? Because E is a state function, P is a state function, volume is a state function, right? At equilibrium. So H itself is a state function. So that is the main message from today's class. And we are going to prove this in a moment. We haven't proved this yet. That delta Q for a constant volume process, reversible or irreversible, is dE. It's a change of a state function, the internal energy. And delta Q for a constant pressure process, reversible or irreversible, and let me write it down actually, or any path, is equal to dH. That makes these things quite useful. And actually, going back, Shah, to your question, it is still used in the opposite manner. Calorimetry allows us to calculate how much heat we give into a system. And doing calorimetry, if you could calculate the heat given to a system, you could go back and calculate the enthalpy change of a system, something like that, right? So it just, these two equations open up different ways for us to make thermodynamics useful. So we have to prove this, that delta Q at constant pressure is D of E plus PV. How do we do this? Does it, what?
This dP is for the system itself, right?
It's a good point. So for this constant pressure, since it's a constant, this is a subtle point. I'm very happy you brought it up. It's a constant pressure process, and I'm assuming that P system is the same as P environment. And if you think about it, last night I got very confused. Like, why should I assume that? No, it's okay. And that's what we're assuming, that this is a constant pressure process, because you might say, well, it's constant pressure, but maybe it's not at equilibrium, right? No, it's a constant pressure process. We are assuming P system is the same as P system. Okay.
So that.
Yeah. So tell me, how should I prove this?
Oh no, I'm saying
Okay.
the consequence that means that process needs to be done was decided.
Only pressure. Nothing about energy, nothing about temperature, anything like that. Only pressure is constant. It's an environment where all pressures are constant.
Yeah, so in order to satisfy that, then
Mechanically quasi-static,
yeah.
not thermally quasi-static. Okay, so part of it is like that. You can think of it that way. So it's not full equilibrium. Mechanically, we have a state of constant. Yeah, so mechanically it's in equilibrium. You can think of it that way. So what I want to show, and I want someone to help me work through this, is that delta Q is equal to D of H, which is defined as D of E plus PV for constant pressure. How should I prove this? Stephen, you had submitted, where is Stephen? You had submitted 2 homeworks, right? 2 copies. So I graded both. You got the same in both. So it's okay. Sia is not here today. And you are Zhao Chang?
Yeah.
You want to take yours? Okay. Well, you can help me. How to prove this? Oh, wise guy. Sure, do the math. What is the math? Tell me. It's not that hard. It's easy. Tell me. DE is equal to? Let's start with this one. DE is equal to delta Q minus PdV. Okay? And I'm saying that just like you asked, that P is the same. So I'm not going to write P external or P system. Okay, you got us started. What should I do from here? It's a constant pressure process, right? So I can do a magic here and say minus VdP. Why? Because in this example, dP is equal to 0, correct? It's a constant pressure process. Therefore, dE is equal to delta Q minus PdV minus VdP, or delta Q minus D of PV, right? At constant pressure. If it was not constant pressure, we would not have been able to put in the dP is equal to 0, right? And there you go. Or delta Q is equal to D of E plus PV at constant pressure. That's our H. That's how we defined our enthalpy. So enthalpy is a state function. Soon we will see the natural variables for enthalpy. So far we have seen natural variables for S and E, right? I'm still trying to remember everyone's names. Matt. No, Matt, I already asked. We'll leave that. No, it's okay. Let's go to Lydia. Lydia, what are the natural variables for entropy? And NVE. Good. And Elizabeth is there. Elizabeth, what are the natural for E? S and V, correct. And so this one we should remember. It's not too hard. All you need to remember is S of NVE, and the other one follows. For H, the natural variables are kind of funky. We will see in a moment that they turn out to be, not in a moment, in a couple of classes, that they turn out to be S, N, and P. It's highly non-trivial, right? And I always forget it. The only reason I remember it, because last year there was a student in thermal who would sit always in the front row, and he remembered it, so now I remember it. He works with Leah Dodson. I'm blanking on his name. Yeah, but yeah, I see him in the streets now, and I ask him what are the natural variables for H, and he says S and P. He just remembers it now. So if you were doing an experiment where the control variables were S and P, why do we care about these natural variables? Because if it's an isolated system at constant NVE, then the direction of spontaneous change is one which increases entropy, right? If we are doing something at constant S and V, then the direction of change is decreasing the energy. Later, we will see a similar principle applies to H. If you're doing an experiment at constant S, N, and P, then you can think about H. And it's not obvious at this point whether H should be minimized or maximized. Turns out it should be minimized. Okay. We will see later that natural variables of H are S, N, P. We will see it in two ways. One, we will see in a very simple algebra manner, just it will fall through the manipulations that you can see that these are the natural variables. Then we will see through Legendre transforms later. So all these three are Legendre transforms of each other, which we did in the first homework. So they are connected deeply. And there will be a couple of more such transforms we will see later. Any questions about this? Okay. So again, let me summarize what we have shown so far. We have shown that delta Q, constant volume, reversible or irreversible, is equal to dE. Delta Q, constant pressure, reversible or irreversible is equal to dH, where H is defined as E plus PV. Okay, so these are important relations. Last time when I did this, I came next time and I gave a pop quiz, and 40% of the people got this wrong. So I might give you a pop quiz next time, but just remember this, okay? And the first one is very easy to prove because all you need to do is to write down the first law of thermodynamics. Second one is a bit harder, right? Because we had to do that thing of adding dP is equal to 0. It's a bit harder. Now, these equations are super important because they connect us to something fundamental to thermodynamics, which is known as heat capacity. What is heat capacity? How do we define heat capacity? Sarah, how should I define heat capacity? By a certain amount, right? So heat capacity C is defined as Q by T. But now we have our superior knowledge of thermodynamics, right? So on the top, can we write dQ? No, heat is a state function. So we'll have to write delta Q divided by some delta T, right? This is our heat capacity. So this is the most general definition of heat capacity. We can define heat capacity at constant volume, delta Q by delta T for a constant volume process. We can define heat capacity at constant pressure, delta Q by delta T at constant pressure. So if for a moment you forgot about the bottom two equations and I asked you to just look at this one, would you say that heat capacity of a system depends on only the state of the system, or should it depend on how you prepared the system? In reality, we know that heat capacity is not path dependent, right? You have some material. What is one of the highest heat capacity materials that you can think of? Water, right? What is some of the lowest heat capacity material you can think of? Sand, actually. So in deserts, the temperature range is huge. In the night, it gets very cold. In the daytime, it gets very hot, right? Because sand is just very easy to heat, very easy to cool. Water takes a lot of heat to heat it up. It takes a lot of heat to pull it out in order to cool it, right? So for example, in India, where I come from, if you go to a place like Bombay, which is on the ocean, the temperatures kind of stay the same. If you go to a desert town, the temperatures go easily from like 120 Fahrenheit or 115 Fahrenheit to as low as 20 Fahrenheit or 30 Fahrenheit in the same day, which is crazy, but not in a town next to water because water has so much high heat capacity. But if you just look at even the bottom two equation, delta Q by delta T at constant V, on the numerator, you have a delta Q, which is a path function, right? So if you just look at that equation, it looks like it is something that depends on path. Why should the heat capacity depend only on state? But given these two nice equations that we just showed, and let's call it equation number 7 together, equation 7 shows us why heat capacity at constant volume is a state function, right? Because this thing is now partial E by partial T at constant volume, right? And E is a state function. If E is a state function, then partial E by partial T is a state function, right? Therefore, heat capacity at constant volume is a state function. You don't need to worry about, you don't need to say, this water has heat capacity this much because this is how it was prepared, right? You don't, and it's right, she's laughing. But it would be, path functions are bulky, right? They're clumsy. You have to account for the whole history of how you prepared the system. You don't have to worry about that anymore. Sorry, so this is going to be delta H. Notice that I cannot make any claims about other heat capacities, right? You could define some heat capacity in some other random manner. I don't know. That there is no guarantee that that would be a state function, but these two are state functions. Heat capacities are state functions because they are derived, they are defined as partial derivatives of state functions. I want to tell you a little bit of a story about heat capacity, which I like a lot. In the years that I teach 687, I go through heat capacity in great detail, deriving it from first principles and StatMech. Next year, I don't know if it will be done or not. If you want to learn about it, you can come to my office and I can tell you. But heat capacity is kind of fundamental to why quantum mechanics and statistical mechanics were developed. Okay, so it turned out that people were able to measure, and this is again out of syllabus. So if you're looking at it later, don't worry about it. But I find this very, very interesting that something like this existed. If you measure heat capacity versus temperature for almost anything on the planet, as you go to very, very high temperature, the heat capacity becomes close to 3 nR, number of atoms multiplied by gas constant. And we will show that in a moment as to why that is the case. Because everything starts to behave as an ideal gas, right? If you increase the temperature very much, things expand, the density becomes very low, right? Things become like an ideal gas. This has a name. Anyone remembers the name for this? It's called a law. It's called the Dulong-Petit law. If you don't remember that, that's great. I mean, who cares? It's some law. We can call it Anjali-Sarath law. It doesn't matter. But what was more interesting is that people would measure heat capacity and they found a very peculiar behavior at lower temperatures. Heat capacity behaved like this. At 0 temperature, heat capacity went to 0. And classical mechanics was unable to explain this. And people would fit this curve and they found a beautiful fit to a first approximation to something that went as cube of temperature. And when, for most materials, for insulating materials, it would fit as AT cube. And when they went to metals with electrons, the fit was AT cube plus BT. Okay, so in StatMech, you can derive this from first principles as to why is heat capacity this. Turns out this comes from phonons, and this comes from electrons. There is a third part which is related to electron-phonon coupling, which is actually people still argue over it. Things like that. Anyone here followed the story of LK99? No one? The superconductor of this summer, right? When people claimed, like Twitter went crazy over it. It's like, oh, we have a high temperature superconductor. And there they had to really think about electron-phonon coupling and things like that, right? So yeah, it was fake in the end. It was actually an anti-superconductor. It conducted worse than most materials out there. So using quantum mechanics, and you can think about it, you can explain this behavior that why as temperature goes to 0, the heat capacity goes to 0. And the simple answer is quantization of energy, right? Heat capacity means how much heat do you have to give to a system in order to change its temperature by a small amount. If the temperature becomes very, very small, you cannot just give any heat and expect that the system will start vibrating faster, right? Because there is a quantization. You have to give heat at least h cut omega for something to happen, right? So if the temperature becomes, so this was the first time people saw that, and I'm not kidding, this was one of the first, I think it was Einstein or maybe someone else who was like, wow, we really need quantum mechanics, because without quantization, without the concept of quantization of energy states, we cannot explain this. And then people were able to do the math. Einstein was a bit lazy. He did not get the correct expression. Einstein in 1905 derived his heat capacity went to 0, but it went to 0 too fast. It went as an exponential curve. So Debye, Paul Debye, who also won the Nobel Prize, got this correct behavior of AT cube. And you will study all this in StatMech. But I find this quite interesting because it was really a triumph of StatMech and quantum mechanics that had to come together to explain something like this. For us, heat capacity is something we can measure in experiments using calorimetry, right? Calorimetry is one of the easiest thermodynamics experiments you can do. And we can measure it, and that's why it's important. So okay, so now let's come back to syllabus. Back to 684. We just showed that CV, heat capacity at constant volume, is partial E by partial T at constant volume. Heat capacity at constant pressure is partial H by partial T at constant pressure. Should one of them, should they be equal? Should they be different? Should one of them always be larger than the other one? What do you expect?
Second one would be larger. because pH equals to E plus PV.
Uh-huh.
So that's why CP is always.
So Subhadeep is absolutely correct that CP is always more than CV, and but now you have to be careful, Subhadeep. Your idea was that H is equal to E plus PV, right? And then you're saying, well, pressure is positive, volume is positive, so H is more than. Why is the reason that Subhadeep's argument is not entirely correct? Because what are we holding constant while differentiating, right? So very good point. We are going to work through that for an ideal gas, but yeah, I really appreciate you answering this. I also thought that, but then I was like, wait, partial is. For an ideal gas, it won't matter. But for everything else, it actually does matter. So you have to be careful. So it turns out that heat capacity, CP is always more than CV. Let me prove it to you intuitively as to why that is the case through an actual thought experiment. Then I will show it for an ideal gas. Later, when we get to something called Maxwell relations, you can derive an exact relation. What is the difference between CP and CV? Okay. So let's think about it physically. You have a container of gas and you are giving some heat into it, right? And heat capacity is how much heat do you have to give to it for the temperature of this gas to raise by 1 degree. Imagine a case in which this container is fixed. Let me draw it over here. So constant volume, it would look you have a container, you have a cover on the container which cannot move, right? So you have some gas and you gave some heat to it, delta Q, as opposed to constant pressure, where you are also giving some heat to the system, delta Q, but now it's a piston which can move up or down. Okay. So in this case, in constant volume, the piston is fixed. In constant pressure, the piston can move up and down. So in the constant volume case, when you give heat to the system, all of it goes into increasing the energy of the gas molecules. In the constant pressure case, you give heat to the system, some of it will go into moving the piston up, right? So which case you are getting more bang for your buck? It's in the constant volume, right? In the constant pressure process, you give some heat. Not all of the heat will go into increasing the temperature of the system. Some of the heat, let me write it down in here, some of the delta Q will go into changing the, not changing, into moving the piston. In the constant pressure process, right? In the constant volume process, all heat goes to gas molecules. So for the same amount of temperature change in constant volume, you need slightly lower delta Q than the right one. Okay, so this is the intuitive argument. Does it make sense? If you ever have me on your qualifying exams, I'm going to ask you this. I promise. In fact, when I go to give seminars in other universities and they send me out for lunch with graduate students, and I end up asking this to them, and I can tell a good sense of the quality of the thermodynamics institute. Everywhere, there will be some places where the students will jump like, of course, it's obvious, you can move the piston up. Not all the heat goes into the volume, into increasing the temperature. Some of it just goes into doing. So you're doing work against the piston, right? That's the idea. So if you think about first law of thermodynamics, that tells you delta Q, sorry, dE is equal to delta Q plus delta W. So in the constant volume process, this thing is zero, right? In the constant pressure process, that thing is not zero. So not everything is going into E. Some of it is going into W. That's the idea. So that's the intuitive proof that you should think about until it makes sense and it's forever etched in your brains. But let's try to see for an ideal gas how we can do this. Yeah.
So, but you said for the case of ideal gas, the two are the same, CV and CP are.
No, it's always, CP is always more than CV. For an ideal gas, we can use the trick Subhadeep suggested. We'll see in a moment. And for an ideal gas, whether you do partial H by partial T at constant P, or whether you do partial H by partial T at constant V will not matter. You will see in a moment.
So is there a case that we use CV even though volume changes?
Say again?
Is there a case that we use CV even though volume
No,
changes?
no. You cannot. Then it's some arbitrary heat capacity, and I don't even know whether it's a state function or not. The only two heat capacities that I know are state functions are CP and CV. If it's a process where you're giving heat to a system and it's neither constant pressure nor constant volume, then you're screwed. Game over. It's terrible, bad news. So stick to constant pressure or constant volume. It's possible that you can show it for other processes also, but I don't know off the top of my head.
You stated that there's a case to cases.
At least two cases, yeah. So there might be others. I mean, I could make up bonus. Oh, starting this homework, I will give some bonus problems. Please do them. I will grade leniently, and which means that you can score more than 100 on an exam, which is one way to overcome if you lose in any other homeworks. Okay, so there will be bonus problems. I cannot guarantee whether the bonus problem has an answer or not. Sometimes I just give it for fun. At least one time, a bonus problem came close to me writing a paper with this student, but that's another story. So yeah, but you should try. This could be a bonus problem. Think of other scenarios where heat capacity is still a state function. Okay, good. So let's find Cp minus Cv for ideal gas. I will write down the answer before we prove it. Answer will be quite simple. It will be Cp minus Cv is equal to Nr. Okay, where N is the number of molecules or moles or whatever you have, the extensive quantity multiplied by gas constant. So let's prove this.
But they are the same because it's constant. I think derivative.
What do you mean Cp is same as Cv? No,
No, when we take the derivative. Oh, no. Yeah.
come on. Yeah. Okay, good. So in order to do this, I have to start by thinking about E. The natural variables of E are SVN, right? But we are going to do something different here. We are going to express E as a function of TVN. We can do that, right? Nothing is stopping us from doing that. This is not a fundamental equation. And before you all forget, remember we talked about fundamental equations. S is equal to S of NVE, E is equal to E of NVS, E is equal to E of NVT can be written down, but it will be a differential equation, right? It's not a fundamental equation. We also talked about equations of state, remember, as to how 3 equations of state can give you fundamental equation. If you have 2 equations of state, you're missing a fundamental equation. We derive the entropy for an ideal gas, things like that. So we will write down E in this form, and just let me mention here, this is not a fundamental equation, and that's okay. No one is stopping us from doing that. This is the form that turns out to be useful in this case.
Excuse me.
Yeah.
Can we prove this on one line, like there is fixed, Cp for monatomic gas is 5 by 2, and Cv for monatomic gas is 3 by 2. So
Yeah.
we just subtract them and just put them.
Sure, for monoatomic gas, but how do you know that Cp is 5R by 2 for monoatomic gas?
It's like came from experiments.
Came to me in the dream.
It can, that's fair enough, but let's become a bit more rigorous, okay? You're correct. So that's the thing about thermodynamics. Most of the things in the semester should make sense to you, like, oh, I know this, but they just become more rigorous and abstract, right? You're doing everything from, starting from S is equal to S of NVE, you can derive the whole phase diagram. Starting from our postulates, you can derive everything, right? Including this. So what you're saying is correct, but you're assuming a lot of knowledge there, either experiments or equipartition or something like that, right? So let's do this. Furthermore, let's assume constant N system, okay? So we are not going to change the number of particles, no chemical reaction is happening, okay? So in this case, E is equal to E of TV. We don't care about N, it's just a constant. So what can we do now? We can say dE is equal to partial E by partial V at constant t multiplied by dV plus partial E by partial t at constant V multiplied by dt. Does partial E by partial t at constant V have a name? That's CV, right? That's CV. So this is CV dt. Does partial E by partial V at constant t have a name? Well, it does not. It looks like pressure, energy divided by volume. So we are going to call it, it shows up later. So I'm just going to give it a name for now. I will call it pi t or internal pressure. It's just a name and we will talk about internal pressure later. Internal pressure, which is defined as partial E by partial V at constant t. So one moment, equation number 8 is true for any material at constant n. Okay, we have not assumed ideal gas or anything so far, right? All we have done is to write down E of TV and differentiate it, right? That's all we have done. What I'm going to show now is that for ideal gas, pi t is equal to 0. How do I show that? Any ideas? That is partial E by partial V at constant t is equal to 0 for ideal gas. Any ideas? This is where Subhadeep is going to scold me and be like, no, you are using experiments now. My method was better. What is the energy of an ideal gas? We saw this expression when we did equation of state. We have seen this equation of state. Remember, for ideal gas, Murray set us off by telling us the ideal gas law. Remember Murray? And then there was the equipartition, right? Which came to us from experiment. So we are using some experiment in that sense. E is equal to 3 by 2 nRT, right? What happens to this if you differentiate it with respect to volume at constant temperature? Is 0, right? There is no volume dependence. So an ideal gas, the energy of an ideal gas does not depend on how much volume the ideal gas is occupying. It only depends on the temperature. Why? Because ideal gas does not talk to each other, right? I mean, even if you don't believe in this being measured, this should make intuitively sense if you think about how we defined an ideal gas. Particles are not talking to each other, things like that. So therefore, pi t is equal to 0 for ideal gas. Let's call this equation 9. So put 9 in 8. What do we get? So equation 8 was dE is equal to pi t dV plus CV dt. True for everything. And if you put pi t is equal to 0 in it, you get dE is equal to CV dt, true for ideal gas. Once again, we have something interesting. Note how we defined CV. How did we define CV? That was partial Q by partial T at constant volume, right? Which turned out to be partial E by partial T at constant volume. And this was true for everything. True for everything. What is CV for an ideal gas? It is actually dE by dt. And again, you can see why thermo can play tricks on you, because it's very tempting, right? When you will be in the final in-class exam and you will be stuck terribly, you will be so tempted to make assumptions like this. You'll be like, partial, it's all the same. Let's just change it into a D. But you cannot do that, right? There is a huge difference here, right? For any material, for any generic material, CV is partial E by partial T holding volume constant. For an ideal gas, we just showed that CV is just dE by dt. And we know what is E. E is 3 by 2 nRT, right? So what is CV? And now we come to Subhadeep. So that's where he's going to jump. Be like, I told you this already. Why did you derive this? I mean, CV is equal to 3 nR by 2, right? For ideal gas. Since E is equal to 3 nRT by 2. So that's CV, but what we are really interested is in CP minus CV, right? And let me finish this and we are done. It's just one more line. So CP minus CV is partial H by partial T at constant P. And this is where I cannot use what you suggested, Subhadeep, because it has constant pressure. So we have to start a bit carefully. Partial H by partial T at constant P minus CV. What did we just show CV for ideal gas? That is minus 3 nR by 2. What is H? H is equal to E plus PV, okay? And I know I'm going through this a bit fast. Go through it. If it's not clear, send me a Slack message. I will do this part again. But if you go through it, I promise you all have already done harder stuff. So since H is equal to E plus PV, this becomes partial E by partial T at constant pressure plus partial PV at partial T at constant pressure minus 3 nR by 2. What is partial E by partial T at constant pressure? If you look at this equation, it's again 3 nR by 2. So what do we get? We get 3 nR by 2 plus partial PV by partial T at constant pressure minus 3 nR by 2. These two things cancel out. Now we will use Murray's favorite equation. PV is equal to nRT for an ideal gas, right? So what can we say here now, Murray? We can say partial nRT by partial T at constant pressure. And how much is that one? nR, right? I know I went with this through a bit fast, but just go through it once again at home. So what did we just show? CP minus CV is equal to nR for an ideal gas, okay? This is not true in general, but the interesting thing is you can write down relations for CP minus CV that are exact. They involve partial derivatives of entropy, which is subject to some other stuff. This is where we are going to stop. And please go through this proof, the last part. If it's not clear, I will review it again. So next class is also in person. I will see you here.